So in this example today we're going to be going over what a limit is numerically, and we're just going to be kind of just approximating a limit just using certain tables. We're not going to be estimating it graphically. We're just going to be doing it just numerically, just using numbers and just understanding what the whole limit notation is and all that. So we're going to say assume f of x is defined for all x near c, but not c itself. So then we say the limit as x goes to c of f of x is equal to L. And it's equal to some number L, we're going to say. And that's the way you pretty much say this whole limit notation is the limit as x approaches c is equal to some number L. And one thing what we want to keep in mind here is this is just going to be this is just going to provide evidence of a limit, but it does not prove that a limit exists or even has a given value. So this is just a really rough approximation of what a limit is. It proves that there might be a limit, keyword might, but it does not prove that it even exists or even if it has value at that point. So the first thing we're going to do is make a table of values close to some number, close to the number x. Actually, not close to x, close to some number c, sorry. Close to the number c, which is right there. So we're going to make a table with values bigger than c and a table with values smaller than c. And if both converge pretty much at the same point, like if you're plugging in numbers bigger than c and it looks like it's getting close to 3, and you're plugging in numbers smaller than 3 and it's approximating the same point, it's converging to the same point, then you know that the limit exists. Or you just, that there's going to be a limit, and it's just going to provide evidence of a limit pretty much. So let's just do a couple examples here. So the first example is going to be the limit as x approaches 1 of the square root of x minus 1 all over x minus 1. So as you can see, if we plugged in 1 for this, we'd get 0 over 0, which is undefined. But using using the tables, as I said, all we have to do is just make a table, labels x and f of x, we're just going to make 4 squares. That should be more than enough. So if we make it close to 1, but not, remember, we want to make the x close to 1 as possible, but not 1 itself, because we don't care what happens at c itself, because 1 is c in this equation. We just care what happens around 1. So we could just plug in, 0.9995, and we could plug in 0.9999, or even 1 point. Then we could plug in values bigger than 1. So we're going to plug in 0.00001, then 1.0005. So what we get on we could say the lesser side of 1, we get 0.50. I'll just write it down here. We get, let's just make this table a little bigger, because these numbers, we'll just make this part of the table bigger. So we get 0.500063 and then for the 0.9999 we get 0.500001. So it looks like these two are going to 0.5 or 1/2. Let's just see what these ones react like. So we plug in 1.0001, we get 0.4, we'll just say 5 nines. 4 or 5 nines. And then for 1.0005, we get 4.99938. So as you can see, coming from the lesser part, we'll just put a number line here for 1. We'll say 1 is right here. So as we go to 1 from the lesser side, and as we go to 1 from the bigger side of it, it looks like we're heading to 1/2. And this is what this table proves pretty much. Is if we go to 1 from bigger numbers than 1, because remember we said that 1 is C, and we don't care what C is. We don't care what C is defined as in this function we just care what happens around 1. And if we just look at what happens around 1 itself and really close to 1, we can see that it approaches some limit, which looks like it's 1/2. Now we can't say that it's exactly 1/2. This is just an approximation. It's just a guess, as you can say, that it's 1/2. But from these tables right here, we could pretty much say it's 1/2. So that's just